Yeah, certainly.
Because that'll be more relevant to where I'm at
Yeah,
in my
sure, sure.
classes.
Easy. Okay, I'll pull up both of those then. Let's start with that. So the maximal domain side of things. Firstly, let's see. Functions relations. Functions relations. I think that should be it. Cool. Okay, so your implied or maximal domains. For a lot of graphs, this is just going to be all real numbers. The maximal domain is basically all the possible x values that could fit within the function that you have. And for a lot of functions, there isn't really anything that would break the math when you chuck in any other or any odd x values. There are a few functions, though, that will break, depending on what you substitute into them, and so those are the ones that we have to sort of watch out for there. Namely the logarithm, the tan, then you've got the hyperbola truncus, and the even roots. So let's have a look at those. So for logarithms, the inside of the brackets always needs to be greater than 0, never equal to 0. It has an asymptote at x equals 0, or at least wherever the horizontal translation term will be, if you remember from the graph of the logarithm. The easiest way to think about it is just that the inside of the brackets have to be greater than 0, and you just solve that inequality, and you're perfectly fine with that. No worries at all. If it's easier to think about things in terms of graphs, then if you're good at doing your graphing, you can literally just do a quick sketch of what that graph would look like, the relevant key features being the x domain, and then just look at it from there. That's another way you can work with it. If you have multiple logarithms in your sequence, like between pluses and minuses and so, try not to condense them down. Because if you do condense them down, one piece of information that's lost in that is the fact that the initial function said it's this log and this log. So ideally what you want to do is have them all in their initial state, do the maximal domains of each, and then see where they might cross over. Because if you combine everything down, like you can technically with like logarithms, you do lose that information. Fair enough so far?
Yeah, that makes sense.
Sweet. Tan has similar issues. It also has asymptotes. It has a lot more of them, though. There is a couple of ways that you can find the asymptotes of tan. In the textbook, it teaches 2 unique equations, depending on how complicated your tan graph is. Let me see if I can pull that up, actually. I didn't spend much time learning it because there's a, in my opinion, a more intuitive way of going about it. What you'll notice is, there you go, so vertical asymptotes are given by that equation there, and if you have dilation factors, that changes a bit, I believe. Let's see. Maybe it doesn't. Maybe that's just a factorized version. Vertical asymptotes there. Anyway, it's another equation that you could potentially use to find your asymptotes. My preference has been to remember that vertical asymptotes only ever really occur when you get divide by 0 errors. So splitting up tan into its sine and cos components, you now just get to simplify things down to just saying, where does cos, that denominator, go to 0? This is something you already need to be able to do. You need to be able to split tan into sine divided by cos, and you need to be able to solve circular functions equaling 0. So doing it this way relies on things that you would have to know already, whereas memorizing another equation, this is only ever going to be useful in that particular scenario. So it's one less thing to memorize. Feel free to keep it if you already know it, but this to me seems a bit more efficient with your knowledge. But yeah, we're just setting cos to 0. Do you need a recap as to what's going?
Yeah, where does the 2mn come from?
Yeah, so this is the general solution to circular functions. Do you remember doing much of that?
Not really.
Not really? Sure. Let's pull up the stuff around that then. So functions relations, circular functions, general solution. Yeah, I don't believe we looked at this. I think we just solved when there was a particular domain. The reason you're seeing the 2 pi n added to it, it's basically there to factor in the fact that there are multiple circles, multiple revolutions that you could do around the unit circle. And because we're trying to maximize domain, right, there's no domain given. We're just trying to see where are the asymptotes for all possible real numbers. As for how it works, the steps are largely the same. So you still start solving your circular function the same way you always would. Start by getting it on its own with one of the exact values on the other side. Do your substitution if you need to for any of the complicated stuff in there. You then find your first two solutions. So, where does sine equal negative root 3 over 2? Well, that's going to be there and there because the y values are negative root 3 on 2. And that's going to give you your two solutions there. Now, that's only within the first revolution. If you keep adding 2 pi to all those, you get the next set of revolutions. If you subtract 2 pi, you get the previous set every time. So basically having 2 pi n in there, n is the stand-in for the number of revolutions, kind of. It's a number of revolutions forward if it's positive n, and it's a number of revolutions backwards if it's negative n. So pretty much all you do is you find your first two solutions, slap the plus 2 pi n in there, just make sure that you're defining n as an integer. When you introduce a variable, everyone knows what you're doing by putting in the variable there, but to be more, to have a slightly better answer as far as your examiner is concerned, putting an actual bound on n and defining like what it's actually there for is a nice little thing you can add to it. That's like the bare bones of what we do here. There's ways to simplify it further for some circular functions, but for now, is that okay?
Yeah, that makes sense. Thank you.
Yeah, sweet. So that's what's happening here, right? We know that cos goes to 0 at plus minus pi over 2, or pi over 2, comma 3 pi over 2. Any of those, however you want to do it is fine. And all I'm doing is sort of simplifying things a little bit further. So, the brackets equal your solution. You get the minus pi over 2 over to the other side. So the positive and negative will combine. The negative and negative, I guess that should technically say negative pi, but it doesn't end up mattering because the plus 2 pi n will handle that anyway. Now from here, you have two things. These can actually just sort of condense into each other, because if you think of n being any integer, for n equals 1, you get 2 pi over here, and you get 3 pi over here. For n equals negative 1, or maybe even 0, you end up doubling up on values. So you basically end up taking the common factor between them, is the gist of it, being able to simplify things down.
How would you get the negative pi on 2? Or the positive pi on 2 on the right-hand side?
Like, how do you get to this?
Yeah, because it's not like rearranging the equation.
So we do, you're right, just by the raw math, I probably should have put a negative here. It doesn't end up mattering as such. But yeah, you can think of this as having a negative there. So for instance, if this was like a negative pi plus 2 pi n, if you had like n was 1, then you'd have 2 pi here, and you'd have negative pi here. What I'm trying to get at is any integer value of n, if you go to all the integers both left and right, you end up doubling up on your values by having both of these. And so ending up...
I'm wondering what makes it plus minus at the top rather than just plus or just minus.
What makes it plus minus? Because we're finding both spots on the unit circle where cos goes to 0. It's up the top and on the bottom of the unit circle.
Okay.
So, yeah.
Yeah, I get that.
Sweet. To understand a bit better why we're able to condense things down, we can have a look at the cos simplification, and what we can observe is any two solutions to cos are always vertically opposed to each other, right? Like it's the exact same in the forward direction as it is in the backwards direction, which is why you're able to swap things down to just a plus minus rather than having the positive and the negative version, or the positive and the positive version rather, 7 pi over 6, 5 pi over 6. You can just do plus minus either of those and you'll get there perfectly fine, condensing things down. And what you're seeing here is a further simplification of that, because not only are we able to condense it down to a plus minus, but because one of those terms fully disappeared, you can start doing a bit of factorizing, so to speak. But okay, that's about the general solution side of things. as for the ultimate goal that we were trying to reach anyway, it was to find the maximal domain. All of this was finding the asymptotes. So therefore, when we give our maximal domain, we say everything but what we ended up with. So if x equals pi n gives us all the asymptotes, then all real excluding pi n should therefore be the maximal domain. Fair enough in the end there?
Yes, that makes sense. Thank you.
Sweet. The rest of them should be pretty easier for 3 and 4. Again, it's the whole divide by 0 thing. Anytime you have those vertical asymptotes, divide by 0 is the issue. So if it's divide by 0 that's the issue, where does it go to 0? Well, you just chuck the denominator equal to 0, solve, and then once again, exclude that. It's the exact same concept, but a lot easier to solve because it's not a circular function. Truncus, again, even though it's squared, it could be anything on the bottom. You just set it equal to 0 and then just see where it goes to 0. Same idea. Slightly more complicated are the square root functions. Technically, this expands all to all even roots. So it could be square root, could be fourth root, could be sixth root. All of those will have issues where you can't have a negative inside of the root. All right, there can never be a negative in here. There can be 0, though. So this one's very close to the logarithm, where the logarithm had to be greater than 0. This one has to be greater than or equal to 0, since root 0 does actually exist, 0 times 0. But again, you're just doing that inequality, and you're getting there. The reason why it only works, or only has an issue with even roots, is because when you have odd roots, because you have, like let's say it was the cube root of something, when you start to have 3 numbers that are multiplied back to back, suddenly you are allowed to have negatives that would work out. Like for example, -2, -2, and -2 will give you -8. And that, therefore, you can have the cube root of -8, for instance. You're allowed to have positives and negatives in there, just because of how the sign mismatching works.
And so then how would the domain work for that?
Yeah, so that's just all real. There's no issues with anything there. So it's only going to be the ones that I've highlighted at the top here. This is kind of like a nice little cheat sheet for you to refer to, be like, hey, what are the main things? So if you literally just like print this off in a bound reference or whatever, you don't even necessarily need the work solutions if you don't want to, because you've just got the basics of it here for each of them. So it's good to know that it doesn't have an issue for odd roots, but it also means they probably won't ask a question about it because there's, well, no actual math to be done at that point. You might get a question though, could be interesting. So those are all the fundamentals there. Now we can put it all together into more complicated functions, right? Like things that we don't necessarily immediately know what's going on. I've just gone out of my way to chuck in 3 key things to watch out for. So we've got a root involved, we've got a log involved, and we also have a division involved. Division isn't necessarily thought of as a function, and that is more or less correct, but it is something that impacts what the possible domain could be. So you start introducing divide by 0 errors. If you have a combination of functions, pretty much just pick apart each little piece by piece and work on it together individually. So square root of x plus 2, we want the brackets to be, or the inside of the root rather, to be greater than or equal to 0. So we figure out exactly that. For the log, the brackets had to be just greater than 0, non-inclusive, because there is an asymptote at the 0 spot. And we get the second set of possible x values. The last is the possibility of division by 0. So we're going to chuck the whole denominator, make it equal to 0, and then see what would achieve a divide by 0 issue. I've done all these in terms of, so I've done this in terms of what is inclusive. So these are good domains. This one is now saying what you can't have, right? So x equals 2, if you put that in there, you get a divide by 0. So just keep that in mind, like what's inclusive and what's exclusive. You can put like do not equal signs in there if you want, but that's a little bit less intuitive. We don't really use those a whole lot, so that might just cause more confusion. So just can help to just be like, labeling this as inclusive, label that as inclusive, label this as exclusive in your working out. And then, yeah, putting it all together, you just find the intersection of everything. So we put the two inequalities together. Where do they overlap on the number line? Well, that's just going to be the same as the x greater than 1. Not forgetting, of course, at the very end to make sure that we exclude that x equals 2. And that's more or less how you'd write it up. X includes all that, excludes that. There's actually a CAS function for this as well, for the TI-Nspire. If you literally type out domain and put the function in, comma x, you will get exactly that written word for word. Which you can't really navigate to it via the menus as such. You can kind of. It's in the book button. So it's that book button there. If you tap that, I've actually still got it up from last time when I showed it. Basically, if you just press D on your keypad, it'll take you to the top of the D menu. And, well, just search down until you find domain. Domain. I might even have a copy of it somewhere else I can just show you. Yeah, there you go. So you're basically printing exactly that, and you get it in the in its language. You do want to then put that back into set notation or interval notation to be a bit more accurate with how you answer it.
So that would be what's highlighted in green up at the top?
If you wanted like a picture perfect answer, that's what you'd probably put. You'll still get the mark for this. Like, let's not beat around that. It's more so, again, if you're on that study score edge, that's where you might start to have these small little things in your favor that help. But yeah, and you can also, if you can't be bothered looking for it, you can literally just type out domain, like key by key, using the keypad. That works as well. That's about it for the maximal domain related stuff. There isn't too much that comes up. I only kind of put this one in there because it is helpful to think about, mainly around the logarithm stuff. They do it a lot. In fact, if I pull up I've actually been working on some exam solutions recently. If I pull up that last exam I was just working on, this one here. So this doesn't necessarily look like there's too much involved. And then you see there's 4 marks. And you're like, oh shit, what's going on here then? There's a whole sequence as to how you end up solving this. But one of the things you have to keep in mind at the end is the fact that you have 2 logarithms here, not just one. So that's what I was saying before, which is this one has a domain of 0 to infinity. This one has a domain of 4 to infinity, both non-inclusive. When you get to your final answers of x, just making sure that they both fit, or whatever x solutions you have, fit in 4 to infinity, because that'll be the maximal domain of the whole thing. Fair enough what I mean by that?
Yeah, that makes sense.
Yeah, sure. Cool. Okay. Did you also want a recap of that, or did you want to practice a few questions like that?
I think I just wanted more of a recap.
Yeah, sure. Sweet. Okay. Let's chuck that away. And then
I think the main thing with calculus I'd want to work on was like Newton's method.
Yeah, sure.
Because last year that was very briefly gone over by my school and wasn't in the SAC, so I didn't really take much of it in.
Yeah, sure. Okay. So Newton's method, we looked at it last time. Was there anything conceptually that I should clarify further about how Newton's method is working? Or do you want to just go straight to practicing some?
I think logically it makes sense what it does, but just how to apply it very much confuses me.
Yeah, sweet. Okay, so we have the Newton's method equation here. It's probably the weirdest equation you'll see in methods because you now have these xn's and these xn plus 1s and stuff like that. And you might look at that and be like, well, how do I put that in my CAS? What exactly am I doing here? So as far as actually doing Newton's method, I typically will define it in 3 separate steps. So basically, when you walk into your exam or SAC, you're going to have 3 variables, 3 functions that are dedicated towards implementing your Newton's method. The first function, which I'll leave as a of x, is just going to be equal to whatever function that you want to do the Newton's method on. So in the textbook so far, we had f of x is x squared minus 2 for this particular example. So that's what I'm going to define my a of x squared minus 2. Oops. And again, you can define these as whatever letters you want, maybe ones that you don't use often because then they'll get in the way of things. The next thing that matters in the Newton's method is the derivative of whatever your function is. If you look at the Newton's method equation on the textbook highlighted in purplish, you can see there's that division of f dash. To keep things generic in our CAS, we're going to define a second function b of x specifically as the derivative of a of x. Not derivative of x squared minus 2, but the derivative of a of x. That way, whenever a changes, b will also change with it. Lastly is the actual Newton's method implementation itself, c of x. For that, we're going to write out exactly what the Newton's method equation actually is, which is x divided by x minus f of x over f dash, or in our case, x minus a over b. That gets Newton's method into your CAS, more or less. I'll just pause there until you've caught up with the CAS.
Awesome, I've got it.
Sweet, okay. So, how do we actually use this? xn, in the case of the Newton's method formula, just means whatever the current x value is that you're guessing or using. If it's the first x value, it's the guess, or it's the value that it tells you to start with. Like, let's see, one of the questions. They have one that ever gives a starting point. There we go, 6ii. So 6ii says to start with x naught equals -2. You can see how it's got that subscript on it. N is just going to be the iteration of the current guess that you're using. xn plus 1 at the very start of the function is just whatever the next guess would be. It's the value you would then feed in for the next iteration, should you want to or need to. So in the case of the example that we had up here, did they start with 4? Looks like they started with 4. Yeah, they did. So for us, we would start our Newton's method by just doing C of 4. That's going to give us 2.25, which, as we can see if we look back at the table again, 2.25 is the x1 value. All we would do is keep feeding it back in for as many times as we needed to, depending on what we're looking for. So if we're going to go to a certain number of decimal places, we'll just keep feeding this back in and in and in until we reach that number of decimal places. So you could do your C of 2.25 gets us 1.569, which again, if you look at the table, you'll see that all the values that we repeatedly feed into themselves will continue to match what's on the table, x0, or n0, n1, n2, so on. And it's pretty easy to just feed itself into itself multiple times. You can see that we're now likely at 2 or 3 decimal places. Most of the time you'll be capping out at like 3 or 4 decimal places for when to stop. So that's how you get the algorithm into your CAS. Is that all fair enough?
Yeah, that makes sense, thank you.
Sweet. The rest of the table there, they were just kind of showing the f and f dash values simply because that's what's in the actual equation itself. Now, this is probably the better way of doing it, where you check the x value at every single iteration. Technically, what they're showing you in the textbook is that you can actually just nest it over itself a bunch of times. Yeah, it's less useful though, because that'll just send you directly to the final answer, which you can technically just get by CAS solving. Right, like if I just do menu3.1 CAS solve function equals 0, I'm going to get the same thing. Now it's going to give me both, because Newton's method only really hones in on one of those solutions, because it's the gradient descent on a particular point. But you can see that CAS solving pretty much gives me the answer anyway. So going ahead and just doing C of 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 whatever it was, 4, doesn't really matter. It doesn't really tell me anything new. So a lot of the time what you'll find is the questions that are asked are going to be more around how many iterations are there that you do to get to where you need to go. It'll maybe say, yeah, what else could it possibly even say? It's got to almost always be about iterations. Because some of these questions, frankly, are a bit stupid. Because if you look at what they're saying, they say, find Newton's method to X number of decimal places. You can just CAS solve it and then just say the first number of decimal places that you need, and that does get you the answer. Which is why some of them will say, find x1, what's x2? Start here and then do 3 iterations. What do you get? That way they're forcing you to actually use Newton's method. And in fact, that last one that I mentioned there, where it just says, what is x3 after doing your iterations, that's the one that has historically shown up on the actual exam. So for us, remember, x0 is where you start. You don't start at x1. So x0 is 0. So x0 being 4. x1 is therefore 2.25. x2, 1.56. And then so on and so forth. But that won't be too... Actually, will it? How hard is that going to be to remember? For programmers, people who do code, it's not necessarily too hard to remember that. As far as having other people remember it, the easiest thing you can compare it to when you learn it will be the trapezoidal rule. You've got this little x0 here telling you or reminding you that things start at 0, not at 1. It doesn't really have, you don't have that luxury looking directly at the Newton's method thing because it's all in terms of n. So looking here to see where indexes actually start can be helpful. There might even be a reminder in the actual exam. I'll pull up a tech active, I'll see if I can find one. Let's see, do we have a Newton's method thing? Pretty sure that's Newton's method. Oh, that might be bisection method actually. See if I can find it. It's usually multis, but sometimes they'll give it in like a double I or something like that. Nah, all good. Okay, must be somewhere else then. Definitely not in a tech free. All right, this is always going to be your tech active, which is nice because once you've got it defined in your CAS, as long as you don't clear A, B, C, or whatever variables you want to use, you've just got that loaded whenever you need it. You just redefine A into whatever you want. Like for instance, let's say I want to do it on a cubic. Redefine, actually maybe before I do that, I'll show you what the Newton's method currently looks like. Then having redefined A of x as, I don't know, just x cubed. If we then reprint C, we'll see that that's changed now. For x cubed, we would expect an x equals 0 solution. So once again, let's say we're guessing at 2. That's going to find 1.33. And we should... Oh, actually, this might be... for cubic specifically, this might actually break. Because it's an odd function. Remember we talked earlier about how there was that whole repeating, the oscillating sequence, where you go back and forth between your solutions. This one might not actually work. Let's find out. Yeah, so it slowly gets there, pretty slowly though, because it does have that sort of oscillation going to it. But it will eventually find 0, maybe. But yeah, those are the main questions that get asked there. One of the other things that they're showing in the textbook is actually creating your own Newton's method equations. Those are fairly chill, because all you've got to do is remember to put the n's in there, more or less. Xn rather than just x. So for instance, as long as you know that Newton's method is just x minus the original function divided by its derivative, it shouldn't be too hard to make that happen. Like here, right? So let's see if we can give that one a shot live.
So which question number did you say it was?
So question 2 and 3, those ones where they actually get you to create your own Newton's method formula. This question 2 we'll do live together just so we can quickly validate that it isn't too bad to create these. The only thing that looks weird about it is when you've got the n's and the n+1s involved. Let's see. Okay, so for this question, all we know is that we have f of x is equal to x cubed minus 3, and we want to do a Newton's method equation for it. We're told what it is ahead of time, but we're trying to prove or show that we can get there. How might we start getting there?
Would you then find the derivative?
Yep, derivative, that's it. What's that going to end up being?
3x squared.
3x squared, perfect. That's pretty much it. All we're going to do is put it all together. What do we now end up writing for our equation? I'll also bring up the generic one as well on the screen share if you want to look at that.
Wouldn't it be 2x cubed plus 3 over 3x squared?
Well, yeah, that's what we got to get to, but we're going to try and show that we can get there. And so I've got the generic one up on the screen share. We would start there and then just try to simplify things to make it look like that. So starting with this generic one, how might we write using that?
Would it be x minus x cubed minus 3 on 3x squared?
Really close. Just making sure we're putting the n subscripts on each of those.
Yeah.
So xn, and then what it actually equals is xn plus 1. But other than that, yeah, that's the only weird bit.
How did you get to xn plus 1?
That's the, so if you look back on the screen share, that's the generic. Whatever the equals is always xn plus 1, where the plus 1 is in the subscript. I'll try to make that a bit more obvious in mine. N plus 1 in the subscript itself. Because yeah, the whole idea is looping through multiple x guesses, more or less. That's where we end up. Now to actually create it, to get it to where we need it to be, we can see it's all as one big fraction. The next question, therefore, is how are we going to get it into that big fraction?
You multiply x by like 3x squared.
Yeah.
On 3x squared.
Perfect. Yeah. Just bringing the denominator over to there and then combining all the terms. So 3xn squared, xn is going to be xn cubed. So 3xn cubed. It's minus all of this. So what are we going to have on the rest of the top?
Minus xn cubed plus 3.
Yeah, that's it.
Which would just make 2xn cubed plus 3 on 3xn squared.
That's it. 3xn squared, which if I have a look back, hopefully we got there. 3xn squared, 2x, yeah. Nice. And then, yeah, probably, of course, you want to... Well, ideally, you write it literally exactly, word for word, exactly what it looks like. So rather than have it on the right-hand side, you might have it on the left-hand side. That's a very minor nitpick. But, you know, just to make it super easy for the assessors to look, that looks like that. Got it. Awesome. Mark acquired. Yeah, so there's nothing really too challenging about that. Keep your subscripts in there, and I mean, you already showed me exactly how you combine the fraction down. That's pretty much it. I don't see... Let's see if there's anything else here that's weird. I guess the follow-up to it. So hence find an approximation to that with your calculator. Hence find an approximation for 3 to the power of a third.
Would you approximate what that would equal to and then just show the, like, write out the x0 equals 2, get that answer and just like recreate it until you get a decimal close enough? Because you would assume you would get pretty much the same if you follow the instructions they gave you.
Yeah, no, you're absolutely right. So they're literally telling you what to do, which is sub in x naught equals 2, spam this, and then that'll give you the approximation. My thing is, I'm a bit curious how you actually get 3 to the power of a third out of that. That seems a bit interesting, because you've got x cubed minus 3. Why does that give you an approximation for 3 to the power of a third? So, cube root of 3. Oh, because yeah, okay. Okay, I think I figured it out. Have a think.
X of 4 equals 3 to the power of a third.
An x of 4 gets you 3 to the power of a third. 4 to the 3 is going to be a big number, so not quite going to, because 3 to the power of a third is the cube root of 3.
Yeah, so I put that in and I got the answer, which was like 1.44224957031. And then I started with like C of 2.
Yeah, well, that's good.
And then put in that answer and I believe it's 4.
Like, oh, you're saying like x4?
Yeah, because it says x0 there, it would be x4.
Oh, sure. Okay, that's what you meant. Yeah, gotcha. I thought you meant x equals 4, but yeah, no, you're right. Yeah, so that number of iterations will get you however many decimal places we needed. In this case, it's ambiguous. My question to you is, why do you think that approximates this? Like, what is it about this number and this function that doing this gets you there? Took me a moment to think about. So have a think.
Would it have something to do with the like power of a third and power of 3 cancelling each other out? So you would just have x minus 3. And so
yeah,
I don't know where the thought goes from there.
Yeah, well, you had the same initial thought as me, basically, yeah, which is, okay, so I'm noticing there's this relationship between the cube and the cube root. They kind of cancel. Then you kind of get this 3 minus 3 equals 0. That's interesting. Think about, what does Newton's method actually do? If we ignore what it's telling us to do here, why do we even use Newton's method in the first place?
Because it shows you the, like, I feel like when I learned it had something to do with the units. Maybe I'm wrong in thinking that, but you like multiple iterations of the same graph. I'm not sure.
Yeah, no, so it is an iterative thing. You're right. Where you take essentially a bunch of tangent lines and it gets you closer and closer to something. What are we getting closer and closer to?
A certain, like the gradient at a certain point.
Less about the gradient, although technically speaking, you could then also get the gradient at that spot. Yeah, because when you get closer and closer to a specific thing, you do also have gradient information. Yeah, that's not a wrong answer, actually. That's fine. The answer that is nominally given for the Newton's method is you're trying to find x-intercepts with this. You're trying to find where is that solution to f of x equals 0. So while you could absolutely get the gradient at that spot because you now know that spot, the ultimate goal or the idea of it was to find the x-intercept. And if you think about how we normally do x-intercepts just regularly, it's always just f of x equals 0. If you put a 0 here, the 3 would come over, you'd cube root it. That's why doing the Newton's method on this is going to give you an approximation for the cube root of 3. So it's a funky little thing to have a think about there, like why does it give you what it does? Because that might be that's probably more like an exam question. It'll be like, hey, why does it give us this? Or it's more about things that are around Newton's method rather than just telling you do it and then get to a stage. Those are a bit of the easier questions. Make sense now why it approximates this?
Yeah, that makes sense.
Yeah, cool. Sweet. Okay. So that's that. Is there anything else here approximation solution, yep, same thing. Write your own formula again from that. Yeah, once again, you can see the fifth root of 158. Again, it's just going to be the rearranged version of this equation. Let's see what else. A log. And then, yeah, giving values of x1, x2. That's it, exactly. So, and this one they've told you, hey, you're starting at x0. So the next one is x1. So this one, you can do it if you like, or you can just tell me what the general process would be. What do you think we do for like 6i here?
I define the equation, and then because of what we set up before, the derivative, and then the equation that you would be inputting your x values into are automatically generated. And then I would start with c of 0.6 and then input that answer into another c of whatever that answer is, and that's my 1, and then do that one more time and I would get the second value.
I'll just put a slight nuance on there. So c of this, whatever that solution is x1. I just want to make that clear just in case.
Yes, I did.
Yeah, okay.
Yeah.
Cool.
The only thing is, am I meant to write, if I'm writing out my answers, normally in methods you do exact.
Yep.
But you would be doing approximate for this.
Yeah.
And then if so, does it specify to how many decimal places, or do I just write however many my calculator gave me?
Yeah, so this question is lazy. They didn't specify number of decimal places. They should have specified number of decimal places. They did it here for 5. They did it all here. They were just a bit lazy with it here. You won't actually ever get an exact... Will you get an exact? I think the whole idea of Newton's method is that you are finding things that algebra can't find, so you probably don't even get an exact. Let's see, so if we even
what does the 6ii say then? It says something about using exact values.
Well, that one's a quadratic, so that one well, I guess it could be something to the effect of a quadratic that would get you there with algebra. Let's see what happens. So if we test the 6i just in case and see if that gives us exact. I might just be wrong.
The double I or just the singular I?
Well, double I tells us it's going to be exact anyway, so we kind of already know that. I'm curious to see if regular I is going to give us any exact, or if we kind of just have to use decimals. Because in the real world, like different functions and even like logs are pretty typical for it, where a lot of the time you won't really get exacts. So let's see if we, and cubics especially. So got that. Cool. And then they just say 0.6. Okay, well there's an exact there. Yeah, okay. You do get exacts, but they get a bit ridiculous. So maybe that's why they didn't say to use exacts there, because it's just going to get more ridiculous than anything else. But yeah, that's the whole idea there. I'm assuming if we do double I, the exacts will be reasonably writable. But yeah, I guess the intent, like every time I've seen this in an exam, they've never really required exact unless the exact is super easy. It's usually going to be the case where it's fully decimal. Even in like your multis, they'll say which of these is x2, and it'll give you like decimal versions of that. Okay, is there anything else in here? Log equals that. You're given solutions in the interval. That's okay. Get the Newton's method formula. Tangent equation. Yeah, there isn't much that's actually really Newton's method here. This sort of stuff is just broadening again the idea that Newton's method at its core is just a bunch of tangent lines over and over, so they're just kind of getting you down that path. Starting with that, get exact value, show that a is greater than 4. This might be a nice sequence to go down. Yeah, let's see where we end up with in question 7. It's kind of a blend between actually doing Newton's method and then like where it sort of came from, the theory behind it. At least that's what it looks like so far. Okay, So your natural log is equal to x over 4. Oh, hang on. Yeah, natural log x is equal to x over 4.
How would you define that? Oh, would you be defining the equation further down?
Yeah, so when it comes to determining the formula for Newton's method, yeah, it'll be in part B where we define it first.
But would you be using the natural log of x equals x over 4 or the f of x equals natural log of x minus x over 4?
Yeah, I've just seen that now. They have actually done that for us, which is redefine it as the f of x there. So that makes more sense. Yeah. So it's natural log minus x on 4. Yeah. Determine the values of x for which f dash is greater than or equal to 0. That shouldn't be too bad, especially if we have a cas. How are we going to go about doing that?
I would just do a solve that b of x is greater than or equal to 0 and
Yeah.
then solve for x.
Yeah, perfect. That's even better. You're already using functions that you've already defined in there. So if you define your a, you don't even have to go through and go d dx. You do already have it. Nice remembering that you have multiple of those that you can use. Very good.
Yeah, so then would it be 0 is less than x, and which is less than or equal to 4?
Let me just get there and we'll have a look. So, 3, 1. So it was the b of x, and we wanted to do it was greater than or equal to 0. Yeah, between 0 and 4, not inclusive of the 0. Is that what you had?
Yeah, that's what I got.
Yeah, sweet. Awesome. Okay, that's that one locked in. Next up, get our formula for Newton's method. So that'll be the same thing as we did last time, creating our formula. You don't necessarily have to get it over the same fraction if you don't want to. They don't really specify, and it's not required in your simplification steps either. I was going through the exam formula, the exam solution report, and they're sort of wishy-washy between whether they bother to put it over the same denominator or not. So
then would I show my working for that, or would I just look at it on the calculator? Or would I know, would I look at it on the calculator to know what I'm working towards?
Yeah.
Like, what would you recommend doing?
Well, this one
how
just
many
says,
marks would you say this would be in an exam?
Well, if it just says determine it, you can just write it out. Unless it says
Okay.
show that, you don't really have to give too much. This would be a 1 marker, and probably realistically just wouldn't be a question on the exam because you kind of just have it. Or maybe it would, because it's only a non-question because we've already defined everything ahead of time. So maybe it would be like a 1 marker. But yeah, literally just typing in your c of x and writing out exactly what that is. Just a reminder of the subscripts that are required. Sweet. Part C, determine the equation of the tangent when x equals e. Again, cas related. This will be a one-liner, more or less. Okay. That gets us to part B. C is about the equation of the tangent. How do we go about doing that with cas?
I just typed in b of e and then hit enter.
Yep.
But then I rearranged the equation so that it would be over one denominator, which I don't know if I did correctly or if it would be necessary.
As in this answer you rearranged?
Yeah, I put it 1 over e minus a quarter.
Yep.
And then I made the same denominator.
Yeah, sure.
So it was 4 minus e over 4e. Because I don't know, I really struggle to know how much is required in a question.
Yeah, like I was looking, as I said, I was looking at the work solutions that the exam at least the 2024 exam. Sometimes they put same denominator, sometimes they didn't. To me, it just sort of means as convenient. Unless they specify like, hey, put it in this form, where, you know, it's going to be like your show that questions or similar, where you have to definitely get it in that form. So far, the verdict seems to be same denominator if you want to, or you could just have it split. As long as everything else is like simplified as much as it can be, then you're fine. As long as you can choose from there if you want
Would
to have.
it be smarter to, like, if it's not specified, leave it and like finish everything and then come back to
Yeah.
put it over the same denominator if you have time, rather than
Yeah, like if you have time, it's a big
okay.
if though. There are a lot of questions. Well, there
Yeah.
are a lot of questions in the exam, and there will be things that you also dog ear that will be a lot easier to like actually get a new mark out of, rather than simplify things a little bit further. It'll be a very low priority thing, and if you're working your way back to that, then you did exceptionally well on the exam. So you'll be very happy that you're working on that if you are. So worth pointing out though, that answer there isn't actually answer for C. C, that gives you the gradient of the tangent. They've said equation of the tangent at that spot. So that's part of the answer, right? You need the gradient and the point for a tangent line. We have the gradient up until now. Do we have the point? We have x equals e. Yeah, getting the y value will be trivial, right? Just chucking the x equals e in as the f of x. And yeah, gradient point formula could take you from there. The one I want to highlight is the CAS actually has a function for this. In the calculus menu, you have the tangent line function. So if you just pop that down and you do the function that you're trying to tangent line, which I believe I defined already, hope so. A of x, comma x, and then comma the x value. So in this case, it's x equals e. And that gets you the full tangent line, and you can see you got that e minus 1 and the quarter that have appeared in as the linear, and they've just put it all over. In fact, that might be exactly what you had for the... Is that what you had exactly for the... Oh, maybe not.
I hadn't worked out the equation of the line.
Yeah, but the gradient portion, this is all the coefficient of x. Is that... Maybe you would have had the e on the bottom?
Maybe.
I'll just quickly check that I've got a of x defined properly. Yeah, that should be good. So yeah, it looks like in this case there is no plus c term unless I'm going blind. That all looks like a coefficient of the x. So yeah, if you had it rearranged, you probably would have had the e on the bottom there. And any other further factorization. Anyway, all that to say that there is a equation that you can just use on the CAS and get it immediately. So it's a nice and little one-liner. Fair enough?
Yeah, that makes sense.
Cool. Here's a funky question. So show that for between 0 and 4 if it's also between 0 and e, and the tangent at a, so a is our new x value that we're taking our tangent at, show that the tangent at a is positive, or has a positive x-intercept. Okay, there's a lot going on there. Tangent at something having an x-intercept. So that's in the Newton's method chapter for a very specific reason, because the whole point is finding tangents and their x-intercepts. So there's definitely a solution set in here that would go through using tangent, using the Newton's method formula. That's one way. The other that we could potentially be doing would be making use of our tangent line formula. Instead of chucking x equals e in there, you could chuck in your x equals a and then try to analyze that from there. That's the one that's probably more intuitive to me, because it brings it back to being a function that we're more familiar with. It's just, f of x equals 0, and that's a lot easier to think about because you're finding x-intercepts. Using the Newton's method for this is definitely possible. The whole formula is built around it. But I think with the time we have, probably best looking at that approach instead. So what I'm suggesting here is instead of having a tangent line formula at a specific point, they're now saying at x equals a, basically. You're taking a tangent at a. So I can't actually type a because we've redefined it. So our tangent is now going to be a g. We'll just use that one. And that there gives us the generic tangent line formula for any g that we plug in. So as soon as I replace g with anything between 0 and 4 or 0 to e, I should therefore get the x-intercept, and it should also be positive. As
So then
far...
how does that meet the other like limitations?
Yeah,
It's
that's
just saying that A has to be between.
yeah, that's the thing that's initially a bit weird to me. Why are they doing between 0 and 4 and then between 0 and e? Because e is roughly, what is it again? Hang on. 3 point,
3.7.
yeah, 3.7. 2.7, yeah. It's roughly 2.7, so why they've got 0 to 4, I mean, maybe it had to do with the logarithm bound of this divided by 4, but I'm not really seeing that. I don't see why that's there necessarily. Yeah, I don't know why there's a double up there, to be honest. But anyway, the more important part is obviously then going to be show that between 0 to e. As for the show that, you can't necessarily just plug in values. One thing you could potentially do is have this equal 0 and then see what you get in terms of g, because this is the tangent line formula, and for function equals 0, you should get x-intercepts. So we go that. Well, actually, no, it should be comma x equals 0, comma x. X is equal to any of those, which, now that I'm looking at it, yeah, it's just your Newton's method formula. Nice. And so now, oh, okay. So here's where the 0 to 4 is going to start making sense. It's this part, this denominator here. As soon as you have it equaling 4, things get a bit weird. From here, I guess it would be just sign analysis, right? So 0 to e, you're then doing the approximation of saying, well, okay, do we have positive over positive? Do we have negative over positive? What do we have? And what we should observe is that over the whole domain 0 to e, the net sign analysis of it is going to be positive. So for instance, you could have negative on top, negative on bottom, and be perfectly fine, which for 0 to 4 suggests that we should have that negative over negative. So let's see. If we had the x equals 0 specifically, you're going to have natural log of 0, which is 1. 1 minus 1 is 0. And you're going to get 0 there. So that's fair because it's the non-inclusive. A value immediately after that would make this slightly positive, and negative. Hang on, is that right then? Natural log of 0 is 1. Natural log of anything other than that should be positive. Why is that different? That should be between 0 and e. Uh-oh. Let me pull up the solutions for this one. Okay. We're in 10H, question 7. I'll change the screen share over in a bit once I find it. There we go. Oh wait, that's different. It's we wanted we were doing D. Okay. Okay, they got to where we got. A is less than E. Oh, it's log E. Yeah, okay. Natural log of 0 is 1. But natural log of E... No, like natural log of 0 is undefined. That's what I was being stupid about. Natural log of E is 1. That's why I was going backwards. Yeah, those things. Those are the weird ones to remember. Back and forth. Bracket 0 or bracket 1, or bracket itself. Yeah, okay, that was what was going weird. Yeah, because natural log of E being 1 means that anything less than E up to a certain point would make it negative because you're going backwards. And that's why on this top bit here, you end up with a negative on top and therefore a negative on the bottom. Negative divided by negative gets you to positive, which is why it becomes a positive x-intercept. There's a bit of a roundabout way there. Are you tracking, or do I need to re-explain that?
It kind of makes sense.
Yeah.
What are we inputting?
So it's said to determine between the range of 0 to E, right? So what we're essentially doing is trying to figure out, okay, so our breakpoint's at E, right? If you have natural log of E, you have 1. 1 minus 1 gets you to 0. So, that's our breakpoint. We've definitely found that. Now, because natural log of E is 1, anything in the bracket that's less than E, up until 0, is going to be smaller than 1. So 1 minus a number that's smaller than 1. And how do we go backwards again? Oh, wait, because this is positive now. Oh, they've refactored this a bit differently. Yeah, sorry. So 1 minus a number smaller than 1 is positive. The x value, the A, is also still positive. And then 4 minus that number smaller than 1. It's all positive here. And that's just going to repeat all the way up until we get all the way to the back of A equals 0. It's mainly this thing that you're keeping track of, because for any value between 0 to E, that's always positive. You don't have to think about that one. It's just this bit here. And the same thing here, right? From 0 to E, that's always positive. We just want to make sure that this always ends up being positive from 0 to E. So as long as you understand that.
Yeah, that makes sense.
Okay, cool. Yeah, that was a bit of a funky one. And I think our CAS had it differently as well. They had A minus 4, but then they've also solved around this bracket. That's why I was getting a bit confused about what was supposed to be negative and what was supposed to be positive. Looking at a different formula. But yeah, that's the idea. I remember this being a funky one last time I looked at it, and clearly I haven't learned my lesson. That's alright, we all learn. Cool, that'll be about as hard as those get, by the way. I haven't seen anything quite that complicated in the actual exam. They don't really do too much with this. The only funky things that I've seen them ask in the exam is actually around whether Newton's method can exist or not. Can you actually use it? And that'll be about the oscillating and the terminating stuff. Need a recap of those? Or you're happy enough?
I think yes, I do remember.
Yeah. Sweet. If not, it'll be on the recording as well, of course. That'll go live by end of the week. Sweet. All right, well, that's about it then. Any final questions for Newton's method?
Makes sense. Thank you.
Easy. I'll leave you to enjoy the rest of your day. Take care.
Enjoy your weekend.
Bye.
Bye.